Any sufficiently advanced technology is indistinguishable from magic.
Welcome, everybody, to another episode of the Into the Impossible podcast, special edition, Think Like a Nobel Prize Winner. We are welcomed and blessed by the visit and appearance of William Bill Phillips of NIST in Gaithersburg, I believe it is, Maryland. And Bill is a titanic intellect, influence, and just an incredible person. He was introduced to me by my friend Mohammed Nasri Abdullah from Malaysia. And he's also friends of past guests on the show, including Jim Gates up at Brown University, but now making his way back to Maryland to be closer to Bill. Bill, how are you doing today?
Great. Good to see you.
It's great to see you too. I just loved your talk when I heard it in the Malaysian seminar that Nasri had us both on. We got little swords from participating sent through the mail. That must have been fun for the post office. But today we're going to talk about a host of things related to your storied career, which resulted in part in you receiving, along with Stephen Chu and Claude Cohen-Tannoudji, of the 1997 Nobel Prize in Physics. For what I remember, this is in my later part of graduate school, as one of the biggest breakthroughs that I'd ever witnessed in experimental physics, which is the creation of trapped cold atoms using laser light. Basically something that I thought would be impossible, but what did I know back then? And as you know, the theme of this podcast is you have to go into the impossible. So currently, Bill is as I said, at NIST, and with his team there, including past guest Nicole Younger-Halpern and other collaborators, he has devised really a phenomenal pedagogical introduction to some of the most exciting physics on Earth. I study the cosmos, so I'm a little bit partial to these things that float around in space. But if you have to do stuff on Earth, do it with a laser. And if you have to do something, do it very precisely. And Bill, that's your hallmark. That's what you're known for. So today you're going to present some slides, and I may interrupt, but it's not rude. Don't think it's rude. Bill points out, if you ever are part of a big family, you know that we interrupt, and we're all family of physicists. And I'm also going to be clicking on and off to take questions from the audience that was submitted earlier. We'll do that at the very end. So I might interrupt, I might not. And then at the end, I might be clicking around. So don't get disturbed. Bill, are you okay with those rules?
Absolutely. In fact, I encourage interruptions. If anything needs to be clarified or expanded upon, I'll very much appreciate an interruption.
Wonderful.
The title of this presentation is A New Measure, the Revolutionary Quantum Reform of the Metric System. And as you heard, I'm part of NIST's Laser Cooling and Trapping Group. Gretchen Campbell is my group leader. Paulette, Trey Porto, Ian Spielman, Ida Tietzinga, Charles Clark, and most recently, Nicole Younger-Halpern, who's been on this show already, are the other permanent members of the group with whom it's my pleasure to work on a regular basis. I'm not only representing NIST, the National Metrology Institute of the United States, I'm also representing the International Union of Pure and Applied Physics, which has been a key player in the development of the international metric system, and I've been spreading the word about the latest reforms. So, what is this revolutionary reform? Well, first of all, science is about what you can measure. At least this is what people like Kelvin said. And in order to express the results of measurements, you need to have units. And as an international scientific community, we have agreed to use the metric system of units, which is formally known as the International System of Units, because this was done in the 19th century when French was the international language of diplomacy. It's the Système International d'Unité, and we abbreviate that as the SI. And the metric system came into being with the French Revolution around the end of the 18th century. And what I'm here to tell you is that just recently, on the 20th of May, which is World Metrology Day of 2019, we have experienced the greatest revolution in measurement since the French Revolution. So what is the nature of that revolution? Well, the metric system, the SI, is based upon what we call base units, 7 base units. All the other things we measure are some combination of these other units. the kilogram for mass, the meter for length, the second for time, the ampere for electric current, the Kelvin for thermodynamic temperature, the mole for quantity of matter, and the candela for luminous intensity. So everything else is some combination of these things. So like joules is going to be kilogram meter squared per second squared, and that's another SI unit. Now, the nature of the reform is that every one of these 7 base units is now defined by fixing the values of constants of nature. Now, in order to explain how this is even possible, I mean, how do we get to fix a value for a constant of nature? Doesn't nature do that? Well, in order to explain how this works, and with apologies to the late, great Stephen Hawking, I'm going to bring you my version of A Brief History of Time. Since, well, as long as anybody has thought about it, seconds were a certain fraction of a day. I mean, there's 24 hours in a day, there's 60 minutes in an hour, there's 60 seconds in a minute. So a second is 1 day divided by 86,400. Well, that sounds great, pretty clear. The trouble is that at least since around 1900, we've known that the length of the day changes. And this isn't just the kind of changes that happen as the Earth goes around the sun. You can average that out and use something called the mean solar day. But the fact of the matter is that things like the tides exert a frictional force on the rotation of the Earth, and that slows the Earth down. Earthquakes can redistribute the mass of the Earth, and that changes its moment of inertia. And because angular momentum is conserved in the absence of an external torque, that's going to change the rotation rate. If ocean currents change, that will also change the angular momentum due to the water. And so the angular momentum due to everything else has to compensate for that. So there's all sorts of reasons why the rotation rate of the Earth isn't constant. And we've known that since 1900. We've actually had clocks that could see that the rotation rate of the Earth was changing since around 1900. In the middle of the 20th century, a wonderful thing happened. We started to have atomic clocks. This is a picture of the very first atomic clock built at the predecessor to my institution, NIST. It was then called the National Bureau of Standards. Well, it wasn't exactly an atomic clock. It was a molecular clock. The ammonia molecule was used to be the ticker in this atomic clock. That was the first atomic clock. Ammonia didn't quite catch on, but a few years later, at the sister laboratory to NIST in the United Kingdom, the National Physical Laboratory, they did something that really did catch on. The first cesium clock. And here's a picture of that from 1955. There's an atomic beam of cesium going down this tube. And what happens is that here's the cesium atom. So just imagine the cesium atom as being a nucleus with a valence electron somewhere outside, all the other inner electrons, and both the nucleus and the electron are spinning, which means they create a magnetic field. And that means there's an energy associated with the orientation of this electron spin in the magnetic field. Now, in an oversimplified version, if that spin flips and points in the other direction, there's going to be an energy difference. And that energy difference corresponds to a frequency. And we can induce this spin to flip by shining in microwaves at just the right frequency. So if I shine in microwaves at this frequency that you can see right here, a little bit more than 9 gigahertz, then this electron will flip its spin and we'll be able to tell that. But if the frequency is wrong, then it won't flip its spin. This is what we call resonance. You've got to have the frequency of the microwaves, frequency of the light, match the natural frequency of the atom in order to get it to change state. So when the atom changes its state after we put in these microwaves, we know that the frequency was just right. Remember, this is an oversimplification. There's a lot more to it than that. But basically, that means that if you get this thing to change its state, then you know that the frequency of the microwaves is this number. In other words, we have defined this frequency in cesium to be this number. And the reason to do that was to define what we mean by a second. So instead of having the second being defined by the rotation of the Earth, which isn't constant, it's now defined by the difference in energy between two energy levels in a cesium atom. And as far as we know, that's always the same. Doesn't change with time, doesn't change with what cesium atom you've got. It's the same everywhere. So this is great. This is just the kind of thing that we want. And this is the current definition of the second in the modern metric system. That is the duration of 9 billion, 192 million, whatever periods of the radiation that corresponds to that transition. And you tell that you got your frequency on that transition by seeing that you made the transition. Well, ever since people started to make cesium clocks, these clocks have been improving. Here's a plot of how good the uncertainty in these clocks as a function of time ever since that first clock in 1955. And here's where the redefinition was made in 1967, and it just kept getting better. But it bottomed out around a part in 10 to the 14. Now you might say, a part in 10 to the 14, come on, that's incredible. And it is. But you know what? At the National Institute of Standards and Technology, your National Metrology Institute, we are not satisfied. And what was the thing that caused this to bottom out at a part in 10 to the 14th? Well, it's the fact that the cesium atoms are moving so fast. If you heat up a lump of cesium metal, which is what we do, until it vaporizes and makes atoms, because that's what we want isolated cesium atoms, they're moving over 100 meters per second. And it's just hard to measure stuff that's moving that fast. So in order to fix this problem, we used this technique called laser cooling that Brian alluded to during his introduction. Now, this is what the laser cooling group is actually known for. That's why we're called the laser cooling and trapping group, is because that's what we've been developing over these years. And it allowed us to make these clocks a whole lot better. Well, I should say it allowed other people to use the techniques that we developed in the laser cooling and trapping group to make better clocks. And today, these cesium clocks are good to a few parts in 10 to the 16. So here's the rest of that curve. And now these things are bottoming out at a few parts in 10 to the 16.
Are there uncertainties on the uncertainty, Bill, or are they just smaller than the dot size?
Yeah, no, yeah, there are certainly uncertainties on the uncertainties. I don't remember exactly what they are, but you would I would say that the uncertainty on the cesium clock is about 2 times 10 to the minus 16, and the uncertainty on that uncertainty is probably about a half of a part in 10 to the 16.
Wow.
But, you know, it's really hard to estimate these uncertainties at these incredible levels, and even harder to estimate the uncertainty on the uncertainty.
Right. And then is cesium kind of grandfathered in as something that make a good choice?
Yes, exactly. So back in 1955, it was a good choice for a couple of reasons. It's got the largest hyperfine frequency of any alkali metal because it's the heaviest. And you want a large frequency because if there's anything that messes you up that's approximately constant, like say a stray magnetic field, it'll be a smaller fraction. So this is really good. You want a high frequency. It's being so heavy means that at a given temperature, the atoms are going more slowly because temperature is just a measure of kinetic energy. Kinetic energy is 1/2 mv squared. So if m is bigger, v is going to be smaller for the same energy. And it's got a pretty high vapor pressure at room temperature. So you don't have to heat it up much. So all these things are in its favor. Another thing that was really important in 1955 that's not so important today is that cesium atoms are easy to detect. They've got a very low ionization potential. That is, it doesn't take much energy to pull the electron off. So if one of these atoms sits down on a metal surface like tungsten that has what we call a high work function, that's the amount of energy it takes to pull an electron out of the tungsten, the electron would rather be in the tungsten than on the atom. So that the electron gets sucked into the metal, leaving an ion, and that ion is easy to detect. So that was really important in 1955. Not so important today because we just shine a laser on the cesium atoms We get a burst of photons, and it's easy to detect that way.
Wow.
And it turns out that cesium is one of the best atoms for laser cooling. So it has turned out to be a pretty good choice. Not perfect, because it's got bad collisional properties, which is one of the reasons why it bottoms out at about part 10 to the 16. But we're going to do better.
Okay.
Okay, so here's a picture of one of those cesium clocks. Don Meekhoff and Steve Jeffords cool those cesium atoms down to less than 1/1,000,000th of a degree above absolute zero. At that temperature, these cesium atoms are moving not at over 100 meters per second, but at less than 1 centimeter per second. They launch them up in a vacuum tube about a meter high. They fall back down after about a second. And instead of having milliseconds to measure, they've now got a whole second to measure things. And this produces these incredible clocks that are good to a few parts in 10 to the 16.
These are fountains, atomic
Right,
fountains.
this is what's called a fountain clock, because you're throwing the atoms up and they fall back down, sort of like one of these vertical jets of water that you see in a little pond or in a big lake. There's one in Lake Geneva.
Right.
And
Las Vegas has a couple of them.
yeah, and so out of sort of recalling the beauty of those fountains, we call this an atomic fountain.
Okay.
So now, so here's a very important thing. We started with something that was basically an artifact, the Earth. I mean, there's nothing special about the Earth, and it changes. And we've changed to the property of an atom, something that, as far as we know, doesn't change, and something that depends on quantum mechanics. And this is a key concept about what we want to do with the uh, the definition of units. We want to get away from things that are arbitrary and go toward things that are fixed by nature. And so you see, we defined what the frequency of this transition in the cesium atom is, and that was the first one of our units, the second, that was defined in this way by, well, it's not quite true, but okay, I told a little lie there. We'll come back to that later. Let's say it was the first one of the units defined by defining a constant of nature. And you see how much better this is. This is always going to be good. The atom's not going to change. Okay. Now, an even better story, a short history of length. Now, time historically was pretty important, but length was really important because it had to do with commerce and construction. If you're selling people things by the yard, then you got to know what a yard is. And the early approach was to use the human body. A merchant would measure out a yard of fabric based on the length of his arm. A foot was a foot. A cubit was the distance between the elbow and the end of the hand. A fathom is the arm spread. Now this was great because you always had your unit right with you. Trouble is, it wasn't very consistent. So if you're buying fabric from a short merchant, you might not be getting what you want. So one approach that ancient people took was they used the body of one particular person, typically the monarch. Okay, so in ancient Egypt, the royal cubit was based upon the length of the pharaoh's forearm. And this is what they used to build the pyramids. But of course, the pharaoh wasn't always around when you're out in the field building something. And so what they did was they made an artifact. They made a rod of stone that was the length of the pharaoh's forearm. And that was the representation, an artifact of the royal cubit. Now, the people out in the field making actual measurements used a wooden standard that was calibrated against the stone standard every month. And the penalty for not calibrating every month was the death penalty. These guys were really serious about
That's
their
worse than losing tenure.
Exactly.
Slightly.
So, but this seriousness about metrology resulted in really good results. The baselines of the pyramids are good consistent to a fraction, small fraction of a percent. They're square to 12 arc seconds. These are well-made buildings, and they're well-made because of the fact that they were serious about metrology. And this idea of having an artifact was extremely widespread throughout the world. In medieval Europe, there were artifacts often cemented into the wall in the town square. Here's a town in Germany, in Regensburg, and that's a fathom. And you can see, by comparison to an American tourist, it's a big fathom.
Wow.
So this is probably a great place to be buying fabric. But if you were to go into the surrounding area, it wouldn't be the same. Now, this is a really vexing problem, but incredibly common. At the time of the French Revolution, it was said that there were something like 100,000 different measurement units throughout Europe, maybe just throughout France.
Yep.
And the revolutionaries figured, we are going to fix this. We are going to have a unit of measure that gets away from all this variability based on artifacts. So what did they do? They chose the Earth as the standard of length. They defined a new standard of length called the meter, and the meter was 1/10,000,000th of the distance between the pole and the equator. And the idea was, well, the Earth belongs to everybody. So this is a kind of a democratic definition. And just to be sure that it's completely universal, it's the meridian that goes through Paris.
Yes.
So in order to figure out what a meter was, they sent out two teams of surveyors. These were top-notch astronomers, in fact, because they had to know where they were in latitude and in longitude. And they measured the Paris, not the Paris, but the Dunkirk to Barcelona meridian, starting from Paris, one team going north, one team going south. And when they came back, they knew what the meter was in terms of the old units, the ancien regime, and they really had done what was hoped for. They had something that was good for all times and for all people. And this is a medal that was cast to commemorate this idea. You see this mythological creature measuring the Earth, and that is in fact what they did. They measured the Earth. Trouble is, it's not so easy to check. And so they made an artifact. And this artifact, platinum rod, is the meter of the archives. In 1799, this thing was made and deposited in the archives of France, reflecting this measurement of the Earth that had been done by these French scientists. And this became the standard of length for all of France. A few decades later, 1875, countries of the world got together and decided to adopt the metric system as their own system of units, and decided they would make a new version of the meter. And they made a rod, you see pictured here, where the distance between two scratches on it was equal to the end-to-end distance of the meter of the archives. 1875. Well, that's when the treaty was made. It was in the 1880s that they finally made this meter. 1880s in France, the physicists in France and in other parts of the world had spent this century learning, among other things, that light was a wave. And one of the things you can do with waves is you can interfere them. And you can make devices. Here's a cartoon picture of a Michelson interferometer. And Michelson was the first one to measure the length of a meter in terms of a wavelength of light. And the idea is that you bring some light in, it goes onto a beam splitter like a half-silvered mirror. Some of it's reflected over here, some of it's transmitted. Both of these beams are reflected back to the beam splitter and combined. And they combine to create this interferogram. So where the waves are in opposition to each other, you have destructive interference and you get darkness. And where the waves are aligned with each other, you get constructive interference and you get something light. If you move this mirror by a quarter of a wavelength, which is a couple of hundred nanometers, then this thing changes from light to dark. So it's really easy to measure something, to measure lengths at the nanometer scale. You're comparing that to a meter bar that's got two scratches on it. Those scratches are 10 or 20 microns wide, and you've got to determine where the center of that thing is with a microscope that has an optical resolution of 1 micron. So it didn't take long before people decided this was the way to measure lengths. But it took until 1960 that they redefined what we meant by a meter. In 1960, they, which was the year the laser was invented, they defined the light from this lamp. You see just this lamp that has krypton gas in it. When you run an electric discharge in it, it makes an orange light, and the wavelength of that orange light was used to define what we mean by a meter.
Mm.
Now, that was the year laser was invented. It didn't take long before people made lasers, the light from which was even more pure than the light that was coming from this lamp. So here is a picture of one of those lasers. This is called an iodine stabilized helium neon laser. The gas inside the laser cavity between two mirrors is a mixture of helium and neon, and then it's locked to a transition in molecular iodine. And everybody used this as their de facto standard of length. By 1983, people had decided we have to redefine the meter because it's defined in terms of this crummy, now crummy krypton lamp compared to this beautiful laser. So we ought to redefine the meter. Now, the obvious thing to do would have been to define the meter in terms of the wavelength of the iodine stabilized helium neon laser. There it is. Everybody's using it. Why not make that the new definition? Fortunately, they did not make the obvious choice. Instead, they made a brilliant choice. They defined the speed of light.
Right.
Why does that work? Because of this universal relationship. The wavelength of light times its frequency is equal to the speed of light, regardless of what the wavelength is. And by 1983, people had learned how to measure the frequency of light. So that meant this worked. If we measure the frequency and define the speed of light, we immediately know what the wavelength is, and we've got a new meter stick that's always going to be the same because this relationship is universal.
Is that de facto then referring the meter to the second because you measure frequency in inverse seconds?
Exactly. But the second is so good, remember? Part in 10 to the 16. Well, maybe not in 1983, but still pretty good.
Yeah.
It was orders of magnitude better than what you could measure length to. So the second, you're absolutely right. You need it, but it's so wonderful that we don't have to worry about it. But it's part of the definition. So you needed to define the second before you could define the meter. So once we know what a second is, then we say that the meter is the distance the light travels in this fraction of a second. And basically, you see what that does is it defines the speed of light to be this number in meters per second.
And I don't think it could have actually, according to sociologists who study this, I don't think it could have been done earlier than 1980. So it's kind of fortuitous that these things came about because, as you know, there was a persistent, kind of confirmation bias effect with measurements of the speed of light that they were all kind of tracking, and then they stabilized, and then there was this big shift down, and that didn't really occur until the 1960s or 70s. So if they had done the obvious choice, as you said, they would have been wrong, right?
Yeah, and the well, people say, isn't it too bad that we didn't define the speed of light to be 300?
Right.
Well, that would have been great, but it was too late.
Right. It's like, it wouldn't be great if pi really was 3.
Yeah. Well, unfortunately, with pi, we don't have the choice.
Right.
With c, we do have a choice, but by the time the decision was made, a change that big in the meter would have made everything that had to fit together not fit.
Right.
Cylinders wouldn't fit in pistons, and it just would have been a disaster. So too bad. It would be great if the speed of light was exactly 300 million meters per second, but it wasn't to be. If only it had happened earlier. If only manufacturing hadn't developed such precision, we could have done better. But that's the way it was. So, but anyway, but look at this. The great thing about this is that if somebody makes a better laser, it's more stable, and they did. Somebody devises a new way of measuring the frequency, and they did. And these are the guys who did it, Jan Hall and Ted Hench, made better lasers and devised ways of measuring the frequency better. It's already incorporated into the definition. You don't need a definition because somebody improved the technology by some huge amount. And these guys did improve the technology by some huge amount, and the definition had no need to change. So here's what happened. We went from an artifact to an atomic constant in krypton, and then to a fundamental constant of nature. This is really beautiful. And with this kind of definition, you don't ever need to change. You get a better atom, and you can lock your laser to that atom better than before. It's all good. And this is what I call the beautiful definition. So the meter has a beautiful definition, and on the 20th of May 2019, we brought this same beauty to the definition of the kilogram, the ampere, the Kelvin, and the mole. So why was that important to do, and how did we do it? Well, to understand that, I want to give you a light history of mass. So, just like everything else, there were artifacts. Here's some polished stones from ancient Babylon. One of these things is called a shekel, and this was the weight for the Babylonian Empire. But if you were to go someplace else, then they're going to have a different set of weights. And so the French revolutionaries figured, we're going to fix this too. And we're going to use this same approach where we make it universal. So they're going to base their new unit of mass, called a kilogram, on the meter. The new unit of mass is equal to the mass of a cube of water that is 1/10 of a meter on the side. We call this a liter. Okay, so the mass of a liter of water is defined to be a kilogram. Great, universal, water is readily available, but just like everything else, there's problems. Density of water changes with the temperature. The water, it's hard to get exactly a liter because water sticks to some surfaces, that is wets it, doesn't wet other kinds of surfaces. You get a little bit of changes in the volume because of that. And so guess what? They made an artifact. They made a piece of platinum. And there it is. That's holding it. That's the kilogram of the archives right there. Look how tiny it is.
Yeah.
That's a kilogram of platinum. Platinum was chosen because it's the densest, or one of the densest of all the materials that we have, which means that the buoyancy of the air doesn't affect it very much. You see, when you're trying to weigh something against something else, if the things have different densities, then you got to account for the buoyancy of the air. So you use the densest thing you can. Well, anyway, that thing was made to be as close as you could make it to the mass of a liter of water. And that thing was deposited in the archives in 1799 and became the standard of mass for France. And then decades later, when the countries of the world got together in 1875 to agree to adopt the metric system, they decided to make another kilogram, made as closely as possible. In fact, they made a whole bundle, and they picked the one that was as close to the kilogram of the archives as they could measure, and that became the international prototype of the kilogram. It's there under 3 glass domes, and this is the last artifact. Now think about this. In the 21st century, so before 2019, in the 21st century, the unit of mass is still this artifact, a piece of metal that was made in the 19th century, that was based on an object made in the 18th century. This is scandalous. That in the 21st century, we are using 18th century technology to measure mass. If someone leaves a fingerprint on the international prototype of the kilogram, all of us will lose weight.
I always point out to my friends that work at NIST, one of my students worked on the definition of the volt at NIST in Boulder. And I always said it's very important because actually one of the most egregious laws in the Old Testament is from Leviticus 19, which you probably know, but maybe not all of my listeners know. You shall not do unrighteousness in judgment, in length, in weight, or in measure. And
right.
actually, the punishment for that bill, you might know this, but many people do, was worse than the punishment for obligatory, like for theft or something like that. It was considered almost as egregious as possible, because an ordinary person is capable of determining if somebody's lying or cheating on them, but they couldn't tell if you were cheating about weight or measure. And so being dishonest was actually a crime against God. So you are doing God's work, literally, in the work that you guys do over there. So I want to thank you. Do you think we should bring back the death penalty for people with improper weights and measures?
Well, maybe just fraud in general. But
Okay.
we'll leave that.
Yeah. All right. Another podcast. Yeah.
Yeah, that's right. Now, interestingly, there's things about honest weights in Magna Carta as well.
Mm-hmm.
So this is something that that people have really cared about for a
Yeah.
long time. Well, anyway, nobody leaves a fingerprint on the international prototype of the kilogram, but it appears that the mass is changing nevertheless. This is a plot of, in micrograms, of how the other kilograms that were made at the same time have changed relative to the international prototype kilogram. And you'll notice that they're almost all going in the same direction.
Mm.
This makes you think that maybe it's the prototype kilogram that's changing.
Right.
Well, actually, it seems like everything is changing, because none of them are, agreeing.
Right.
And the trouble is, of course, the mass of the international prototype kilogram cannot change, because by definition, it's a kilogram.
Right.
But that's intolerable. This was just like the old thing with the second. The length of the second was changing, but it can't, because it's the definition of the second was based on the mean solar day. Well, that's just intolerable. So we have to redefine what we mean by a kilogram. And what we want to do is to use this same beautiful definition, whereby we defined the meter by defining the speed of light. So we want to pick a constant of nature, a fundamental constant of nature, to define the kilogram. Well, what constant is that going to be? Well, in order to tell you that, let me remind you of what I'm sure is the most famous equation in all of history.
Okay.
E equals mc squared. What does this mean? It means that the energy of an object at rest is equal to its rest mass times the square of the speed of light. Now, there's another equation, not quite as famous, but one I like very much, and that says the energy of a photon is equal to its frequency. Photon is just a particle of light, so the frequency of the light times Planck's constant. And you could say, what is Planck's constant? Well, it's the constant that makes this true. And the thing that's important about this is that it's the same for all frequencies, okay? So what does it mean? The energy of a photon, a particle of light, is equal to Planck's constant times the frequency of the light. Now let's take these two equations, set them equal to each other, since they're both equations for energy, solve for the mass. And it says that the mass, now what does that mean, the mass? What it means is, let's say I have some particle, a nucleus. It emits a photon, a gamma ray, and I can measure the frequency of that gamma ray. If I measure that frequency, and if I already know what the speed of light is, because we defined it back in 1983, and if today I define Planck's constant, then I know in kilograms how much the mass of that nucleus changed. In a sense, what I've done is I've weighed a photon. Now, this is really just to illustrate what we could do. We don't.
Right.
We don't weigh photons. Actually, we could and we do, just not well enough. This guy, this hero, Brian Kibble, came up with a way, an electromechanical device that we now know as a Kibble balance. And I'm going to show you how this works in a little cartoon movie. So here we go. So first of all, I want to invite you to think about the old way, the traditional way of measuring mass. Let's say we got an unknown mass on this side of the balance. We put known masses on the other side of the balance until the balance balances. So we keep adding mass on the other side of the balance until it balances, and then we know what the mass is of the unknown mass. We've done this, probably most of you have done this in a lab sometime to measure the mass of something. That's the standard way of doing it.
Yep.
Now I want to invite you to think about a different way of doing this. Imagine that instead of standard known masses, I put a coil of wire on the other side. and I put current in that coil of wire, and I put it in a magnetic field. Let's say I got some permanent magnets here. If I know what the current is in that coil, and if I know what the strength of the magnetic field is, and if I know what direction the magnetic field is pointing, because you get the biggest force when the magnetic field is pointing at right angles to the current, and otherwise you got a cosine factor or something, or a sine factor. Okay, so you have to know all that stuff. If I knew all of that stuff, then I would be able to calculate what the force is that is being generated here, because I just know it from Maxwell's equations. And then if I measure the acceleration of gravity, I can figure out what this mass is, because I'm just comparing the electromagnetic force to the gravitational force. Now, the trouble is, I can't do all those things I said that I want to do. I can't measure the magnetic field well enough. I don't know what direction it's pointing. I don't even know where the current is going in this wire. I know I can measure the current really well, but all these other things are really hard to do. So here's where Kibble comes in. Kibble says, okay, that's great. Let's do another experiment with the same apparatus. Let's take that coil. Let's open up the leads on that coil. And the coil is going to be in the same magnetic field. Let's take the leads from that thing and connect it to a voltmeter. And now move the coil in the field of the magnet. This is what a generator does. You move a current-carrying wire in, well, it doesn't have to carry current. I mean, the current will be generated by the generator. Move it in a magnetic field, it generates current. What we're going to do is measure the voltage that is generated. We're not going to let current flow. We're going to measure the voltage. And we're also going to measure the velocity at which the coil is moving. That's why we call this the velocity mode. Okay? We measure the velocity that it moves at, and we can do that very well. We measure the voltage generated, and we can do that very well. And then we also have this measurement from the other part of the experiment, what we call the weighing mode. So we do this velocity mode, measure the velocity and the voltage, and then we put the current in, and we do this weighing mode. We see how much current is required to balance out the mass, but we don't worry about making all these other measurements, because that other one, the velocity mode, gave us all the important stuff. Here's why. The mass of the object times gravity that's the force being generated in the weighing mode. You multiply that by the velocity from the velocity mode, and you've got force times velocity. That's mechanical power. Take the current from the weighing mode, multiply that by the voltage from the velocity mode. Current times voltage is electrical power. Those two things have to be the same in a proper set of units. So that means we can take this equation that makes mechanical power equal to electrical power, solve for the mass, and now we know that the mass is equal to the current times the voltage divided by the acceleration of gravity times the velocity. So that's our new way of measuring mass. But wait a minute, you say, you're trying to cheat me, because you promised this was going to have to do with Planck's constant. And the reason why this has to do with Planck's constant is because of the way in which we measure current and the way in which we measure voltage. These people, Brian Josephson and Klaus von Klitzing, figured out how to do voltage using fundamental constants. The Josephson effect gives you a voltage across what's called a Josephson junction, two superconductors separated by an insulator. The voltage across that junction depends upon the frequency that is generated when you put that voltage. You get a frequency generated, and the ratio of the frequency to the voltage is 2e over h, the charge of the electron divided by Planck's constant. Klaus von Klitzing found that a resistance, kind of a funny resistance, where you put current in one direction, you measure the voltage in the other direction, the ratio of those two things is a resistance, is equal to a sub-integer multiple of h over e squared. And when you put all those things into these equations, you find out that the mass is proportional to h, just like I promised. Of course, I went through that kind of quickly, but maybe we can go over it later.
If you want to. I just had one comment.
Sure.
When I did in my freshman year, sophomore year at Case Western Reserve as an undergrad, I did the Cavendish experiment,
Yeah.
attempting to measure the gravitational attraction of two spheres, basically. And I remember getting, I got the right, prefactor and exponent, but my values for the prefactor was the exponent. It was like 11 times 10 to the minus 6 or something instead of 6 times 10 to the minus 11. So it was all off. But I remember consoling myself with the fact that capital G, which goes into lowercase g,
Absolutely. Yeah.
is still the poorest known fundamental
Bingo.
constant.
That's right.
Yeah. So how does it not get limited by that?
Yeah. Well, because we don't need to know what big G is. We can measure little g by dropping a mirror, and you make one of the mirrors part of an interferometer. By the way, Case Western, this is where Michelson
yeah,
did some of his great work.
That's right. Michelson-Morley. Yep.
Yeah, and the Michelson-Morley experiment which was a Michelson interferometer. Well, make one of the arms of that Michelson interferometer a falling mirror, and you can count off the fringes as a function of time and measure the acceleration of gravity. You can do even better by replacing that mirror with falling atoms and measuring the Doppler shift of the atoms as they fall, and you can measure gravity to better than you need to.
Wow. Okay.
Not a lot better than you need to, but we're working on improving that as well.
Great.
So that is done right in place. And here is a picture of one of those Kibble balances at NIST, and we realized the kilogram to about a part 10 to the 8th, which is better than the dirt effects that we were seeing over time in that plot of mass differences versus time. And these guys are serious about metrology. They tattooed the values of fundamental constants onto their forearms. These are like those ancient Egyptians. These people are really serious about metrology.
They're armed.
Let's see, how are we doing on time here? We got, well, okay, let me just blow through this very quickly.
Yeah.
Using the same idea, Planck's constant, but a completely different approach, using atoms and how fast they recoil when you hit them with a photon. You can then measure the mass of an atom in kilograms, compare the mass of that atom, which you hit with photons and measure the recoil, to the mass of silicon atoms, make a perfect crystal of silicon, turn it into a near perfect sphere, the most perfectly spherical object ever made on the face of the earth, measure its size, measure the spacing of the atoms in that perfect crystal. If you know what the spacing is and you know how big the object is, you know how many atoms are there. And since you know the mass in kilogram of one atom, you know the mass in kilograms of this thing. And this gives you another way of using Planck's constant to get a kilogram.
Wow.
And all over the world, people have been doing this. So here's dots for where they've done the Kibble balance and for where they've done the silicon sphere. And when they all agreed to a sufficiently precise level that had been set by international committees, then the change was made. And here is a movie that was shown at Versailles when 60 countries in the world voted unanimously to change the definition.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world's scientific community. At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it. Ce l'abbiamo fatta. We have Lo logramos.
Lei sia boli.
Biz bundan ayrı olduk. Proud die.
Biz bunu jassadık. Het is ons gelukt.
We сделали это.
Tasarım.
We gjorde det.
Amerika dia.
Mi smo to učinili.
Dokázali jsme to.
سويناها.
Congratulations. Kamila. Felicitaciones.
Mazal tov. Congratulazioni.
Shatter le lavorisce.
Selamat.
Succes. Parabéns.
Ongela. Momento.
Anguida.
Onneksi olkoon.
Mabruk.
Kapai.
Aiko.
Félicitations. Congratulations.
So we finally did what the French revolutionaries had set out to do, was to make something that was good for all time, for all people. No more artifacts. And for me, the idea that 60 countries would unanimously agree to something, it's the way things ought to be.
Yeah.
It's the way we should do things internationally. Well, there's a final part of the story. The ampere, which used to be the current that produced a certain amount of force, is now a certain number of electrons per second because we've defined the charge of the electron. And this means that E over H and 2E over H are defined quantities. So the metrology of voltage and current is now based on these fundamental constants. The mole that used to be the number of entities in 12 grams of carbon-12 is now just a number. Avogadro's number is now defined. The Kelvin used to be 1 over 273.16 of the triple point of water. We now have a defined value of the Boltzmann constant. And I love this definition because it gets at the idea of the microscopic kinetic energy of things that have a temperature, because KT is a measure of the kinetic energy of a single entity, like a single atom in a gas is going to have that energy of KT. So it brings the idea of temperature down to this atomic quantum level. So I really love this definition. So the French Revolution brought us the metric system, length and kilogram as new units of, meters and kilograms as new units of length and mass. The 1875 Convention du Mètre brought us an international agreement that we would all adopt the metric system. And now, on the 20th of May, which is the anniversary of the signing of that 1875 Treaty of the Meter, we now have the biggest revolution since the French Revolution. All the base units are defined by fixing values of the fundamental constants. And we really have done what those French revolutionaries wanted to do, something good for all time, for all people, except it seems for time itself, because time is still defined in terms of a particular atom, the cesium atoms. And the fact is, we got better atoms now. And we're going to have to redefine the second in taking advantage of these better atoms, which are operating at higher frequencies. Remember I said cesium, one of the reasons was because the frequency is higher. Well, we're going to go to frequencies that are orders of magnitude higher, optical frequencies. Instead of 10 to the 10, 10 to the 15 cycles per second. And this is going to lead to frequency standards that are just going to keep getting better and better. They're already operating at parts in 10 to the 18, and no reason why they're not going to work at parts in 10 to the 20th or even better. So this is still yet to be done. The future of time, well, only time will tell.
Thank you, Bill. That was phenomenal. That was so wonderful. And I've got a lot of questions here. So maybe you want to stop your screen share so we can see you full size.
Okay.
And I'm going to, yes. So I said I wouldn't make any dad jokes this week. We're recording this before Father's Day, but I can't resist, so what do you call 10 to the 23rd, avocados, do you know? A guacamole.
Exactly. Oh, actually, it's another definition of that. Do you know W.E. Murner at Stanford?
No, I don't know him personally, but yes.
You heard the name, right? Well, in his lab, they're typically working with a single molecule. So this is a mole divided by avocado's number, so it's a guacamole. So he's used that joke, but the other way around.
Yeah, exactly.
A single molecule is a guacamole substance.
Well, Bill, you probably know our one of the founders of experimental science, Galileo Galilei. There's a finger puppet. I keep him around. He said, "Measure what's measurable and make measurable what is not already so." I want to ask you, what will we get from optical lattice clocks and all the things that we'll maybe talk about in a part 2 someday? I mean, isn't 10 to the minus 19 good enough? Why not stop there?
And the answer is Not for the National Institute of Standards and Technology. It's not. Why? Why do we care? Well, one of the things that I'm really excited about is that using these clocks, we can test whether the fundamental constants are in fact constant.
Mm-hmm.
So one of the really important constants is the fine structure constant. Now, why is this important? It tells us in a dimensionless way. So in other words, it doesn't depend upon the arbitrary choices we've made for what a meter and a second are. It's a dimensionless number. It'll be the same in every system of units. It tells us how strong the electromagnetic forces are. And since almost everything that we encounter in daily life that doesn't have to do with gravity depends upon electromagnetic forces, all of chemistry, the fact that we're alive, depends upon electromagnetic forces. The fine structure constant is really important to determining what life is like. And the question is it the same from year to year? Well, if you have two atomic clocks and they're operating on different atoms, where the transition frequency in those atoms is dependent upon the fine structure constant in different ways, looking at the ratio of those two clocks will tell you whether the fine structure constant is changing. And they've been doing those experiments, and we now know that the fine structure constant does not change to something on the order of a part in 10 to the 18 per year. And as we make these clocks better, we will be able to nail that down even better. But wait, there's more. Einstein's theory of general relativity tells us that two clocks that are transported into different places, different gravitational potentials, different accelerating fields, whatever, those two clocks will maintain the same ratio regardless of what we do to them. So if I've got two clocks that are up in a satellite and I got two similar clocks, let's say one of them is strontium and one of them is ytterbium, and I got a strontium and a ytterbium clock up in the space station, and I got a strontium and ytterbium clock in the lab in Boulder, and I measure those ratios in both places. If they're not the same, then it means that Einstein's theory, his equivalence principle, is wrong.
Right.
Mm-hmm. Now, something's got to be wrong about something, because right now, quantum mechanics and general relativity cannot be put together in a consistent way. Something's going to have to change about one or both of them. Mm-hmm. A lot of people think it's the equivalence principle. God forbid, but the equivalence principle is a wonderful principle. But if it's not right, then maybe there's a route to getting a gravity consistent with quantum mechanics.
Amazing.
And so if we can find out that it's not right, that it doesn't hold, that'd be fantastic. So these are some of the reasons why we want to make these clocks better.
Yeah. I have a video on optical lattice clocks in Juni's group coming up. So that'll be, I'll link to it somewhere up above. So now I want to take a question.
But let me just say another thing. Junyi, we can't forget about Anna Maria Ray.
Yes.
He's the theory muscle behind these optical lattice clocks.
Yes. Yeah. And that got brought up
together.
Yes.
Just unbeatable team.
Well, maybe you'll introduce me to both. I think I was in a competition once with Junyi to celebrate your hero and my hero, Charlie Towns' 90th birthday. You were probably there, right? At Berkeley, maybe in 2005.
Yeah.
This competition, Junyi, Adam Rees, and me, and it was supposed to be, or many other people, but we came in the top three. I came in number one. Adam Rees came in, your near neighbor there. He came in third. And on the day he won the Nobel Prize, my older brother called me up and said, "Well, you won that battle, but he won the war." I'm still waiting. Although, with my books, called "Losing the Nobel Prize," I don't think it's going to happen. And I do want to talk about the Nobel Prize briefly. I know you're on a tight time schedule. I'm so grateful that you're here at all, sharing your incredibly valuable time. We have some questions from the audience, and just a reminder, audience questions can be submitted on my YouTube channel, Dr. Brian Keating, or Twitter, Dr. Brian Keating, Instagram, same as well. So the first one is actually appropriate for this weekend. Again, another dad joke. So we know about your experience trapping atoms. Have you ever trapped an Eve? Here's another one. This one is a famous one. You should never trust atoms, right?
right? Because they make up everything.
Good job. But there is a serious question from my listener. What is the material inside an atom that's not stuff, that's not quarks, that's not electrons? Is there anything in there? Is it vacuum and void, as Lucretius told us 2,300 years ago?
Yeah, well, this goes to some really cool ideas, which you, I think, know better than I. So I mean, all of us have this picture of an atom with a nucleus and electrons. I mean, the typical pictures, the electrons are going around the outside. They're not really. They're in a cloud. They're sort of everywhere at the same time.
By the way, why do they always show lithium? It always has 3 electrons. Like lithium gets unfair attention.
It's not lithium. It's just an iconic atom. It's because if it were lithium, you wouldn't be able to have 3 electrons in the same orbital.
Right.
So
That's true.
it's just the most visually pleasing atom.
Yes.
Interestingly, with a sort of a Bohr-Sommerfeld picture,
Right.
which is so wrong and yet so powerful that we still keep it in our mind.
Right. And Bohr won the Nobel Prize for that atom.
Right, exactly. And I mean, it's really interesting how wrong that picture is, but how useful and important it is nevertheless.
Right.
Someone has that I communicate with from time to time has a tagline. I forget who said it. A model is a lie that helps you see the truth.
Right. And someone said all models are wrong, but some are more useful than others, or something like that.
Yeah, yeah. Well, anyway, okay. So what's in it? So electrons are fundamental particles, and they have a certain mass, and we now understand that they get their mass from the Higgs field. And you've probably all read about the discovery of the Higgs boson, which was predicted as being something that would come along with this Higgs field that gives things mass. Because it was a question: where does mass come from? I mean, it sounds like a stupid question because things just have mass, but why do things have mass? Well, I mean, I don't even understand it very well, but because I'm just an experimentalist.
Right.
But now we got these things in the nucleus where most of the mass is. Those nucleons are not elementary particles. They're made up of, each one of the nucleons, protons or neutrons, are made up of 3 quarks. The quarks are elementary particles. Now, the mass of the nucleus is not equal to the sum of the masses of the quarks because there's a binding energy. And it works the wrong way. Usually, something that's tightly bound is going to have a lower mass than the sum of the other masses because it takes energy to pull them apart. But because of the weird way in which the forces between nucleons work, it works the other way. Most of the mass of the nucleus is binding energy. It's weird binding energy, and it doesn't come from the Higgs mechanism. It comes from the binding part. So I don't know if that answers the question.
No, I think it does. Yeah.
But
No,
the atom's weird.
Yeah, it is weird.
In
That's
lots of
right.
ways.
And even weirder, Bose-Einstein condensates. So John Albert's one of my listeners, asked the question. Effectively, I'm going to translate it into. He's asking about, is it a 5th phase of matter? What I've wondered is, I once heard a talk. Actually, it might be by my friend Stefan Alexander up at Brown. That basically only fermions are sort of fundamental in the sense that you can make a boson out of 2 fermions, but you can't make a fermion out of any number of bosons, right? So, is there something special about fermions? Is there something more special about them compared to bosons, or are we basically able to kind of separate their behaviors out and treat them accordingly?
Yeah. So I would not agree with the idea that the only fundamental particles are fermions. Photons are bosons, and they're pretty fundamental.
Yeah, and I'm not saying that he said that, but I'm just saying it was sort of a crazy idea that we speculated on.
Yeah. So fermions are really, really important because if it weren't for fermions, this would be a pretty dull world. So fermions are the thing that guarantee the complexity of chemistry. Mm-hmm. If electrons were bosons, then all atoms would just have n electrons in the ground state, and the chemistry would be really boring. So I doubt that it would be possible for us to exist if it weren't for the fact that electrons obey a Pauli exclusion principle, which is the thing that says that they're They're fermions. The fact
Gives
that
us
you can
chemistry.
only
Yeah.
have one electron in the same quantum state.
Right.
Probably not the way you learned it in high school, but it's
Exactly. Right. A little update. Next question comes from someone by the name of Hypergolic, which I don't know why someone would give their kid that name. I think it's a nom de plume.
Right.
He asks, can we use trapping of atoms to produce a quantum Hall effect? Can you produce a quantum? Yeah.
Right. And the answer is yes, we hope. So in our laboratory, my colleague Ian Spielman is the one who's doing the work that is closely related to this. He has made with ultra cold atoms, he has made systems that exhibit a classical Hall effect. And then going to the quantum Hall effect just requires more work.
Yeah. Okay. Great. Good. And the last thing is maybe not politically correct, given that you're friends with Jim Gates, but what do you think about supersymmetry and string theory?
Well, look, neither string theory nor supersymmetry, and you're right, Jim Gates is a good friend, and it just breaks my heart that we haven't seen supersymmetric particles because they ought to be there.
Yeah.
But so far, we're not seeing any supersymmetric particles. And with respect to string theory, it hasn't lived up to its initial promise.
Yes.
But at the same time, I think string theory was an important, and still is, an important feature of modern physics because it gives us a glimmer of how it might be that we could unify quantum mechanics and gravity. It might not be the answer, but at least it gives us a feeling that this might happen. So maybe it's going to be something else. It's not strings, brains, but it seems to me that even though this may not be the final answer, and the other thing is nobody's really come up even with new predictions, let alone even old predictions. That is, not we can't even use string theory to retrodict what what we already know.
Well, actually, Kamran Vafa, my friend Kamran Vafa, came on the podcast about 2 years ago, and he said, no, string theory does make predictions and retrodictions, and it says that the mass of the electron should be greater than the Planck mass and less than a kilogram. I was, oh, that's great. That only gives us, 50 orders of magnitude. But I think you're right.
Not greater than the Planck mass. The Planck mass is immense. And
sorry. No, 10 to the minus 12 Planck mass or something like that. You're right. You're right. The Planck mass is like 10 to the minus 5 grams or something. Okay, so Bill, I know you have to catch a plane. I know you're so generous.
It's not a plane, but I actually have to drive to the place where I'm going. But
so if you'll indulge me,
haven't been on a plane since the beginning of the pandemic.
Wow. I just took one with some kids recently, and it was a real charade. So thank your stars that you haven't had to do that. So I wonder if you'll indulge me with a few more minutes of my final thrilling three questions that I ask all my beloved guests. Do you have a couple more minutes, Bill?
Sure, let's do it.
Okay, great. So the first one has to do with what is called an ethical will, which is sort of an inheritance of wisdom, of benediction for the future, not monetary. And as you know, Alfred Nobel had an ethical will, but he also had a monetary will. The monetary will made the prize, but part of the prize was to do the greatest benefit to mankind, which you have done with your colleagues and many other laureates for expanding our horizons. But I want to ask you your personal ethical will. What piece of wisdom or knowledge do you want to leave to the millions of people around the world who look up to you and so forth in terms of wisdom or advice for their lives?
Well, I don't know about the millions of people. I'm not sure millions of people care what I think, but at least for my children, I can imagine some things that I would like to leave to them. I mean, probably the most important thing is be kind to one another. Do the right thing, even if you don't want to, even if it's hard. Actually, these two things are, I think, already embodied in what is my favorite passage of scripture from the Hebrew scriptures. You probably know what I'm going to say. Micah.
Yep. Actually,
what does the Lord require?
Yes.
To do justice, to love kindness, to walk humbly with your God. So that last part, don't be too full of yourself.
Yeah.
I think it's another feature that's good advice. But now, if I was going to be a little bit broader, as people often ask me, what's your advice for me as uh, a budding scientist? Well, usually my answer is stay curious. Keep that childlike curiosity. I think scientists are just children who never grew out of that childlike curiosity. Don't stop learning. That's maybe a corollary of the stay curious. Those are the kinds of things that. There's one more thing. My father-in-law was a very wise man. He was an excellent woodworker, and he made beautiful pieces of furniture. But sometimes things didn't go quite the way he wanted. And his response was, a man on a galloping horse would never notice the difference. And I think that if you take this as a mantra in your life, you can save yourself an awful lot of worry. Something, I mean, it's another version of the perfect is the enemy of the good.
That's right.
That we have to understand when things are good enough, and you move on.
Yeah, as I think Voltaire around the French Revolutionary times we talked about earlier said, and you're now my second guest in 200 interviews who's quoted from Micah for that very same question that I asked, and this is to Carl Sagan's widow, Ann Druyan, when she was on the show. But as you know, Carl was a very, very prominent atheist, and so is Anne. So she left off the walk humbly. She said, walk humbly, and then she just ended the quote. And I said, you know what you left off? And she said, yes, I do. But I still think it's brilliant. And that gave her so much credit as an atheist to realize that there is wisdom in these ancient traditions.
Absolutely. And look, I know an atheist who has a favorite hymn. So I think we got to be really careful about
yeah, exactly. Okay, well, that was looking forward, hopefully when you hit the biblical age of 120 and beyond, like Moses did. The next one goes a billion years into the future, and I'm going to ask you to look into your crystal ball, and I want to ask you, relative to the namesake of the Arthur C. Clarke Center, which I'm the associate director of here in San Diego. And his movie, 2001: A Space Odyssey, where these primates in Africa, and they come upon this black, ominous monolith, and then it appears on the moon, and we're not really sure what it is. Maybe it's a warning, maybe it's a time capsule. I like to think of it as kind of like a time capsule meant to brag and show the swagger of humanity. And so to that end, I want to ask you what you would put on it. You'd tattoo on it like your colleagues, or engrave into it like the scratchings on a platinum rod or whatever that we spoke about. But I want to ask you, looking forward into the future, what would you put on a billion-year lasting time capsule?
Yeah, well, it's really hard to know. I guess that so we're not asking the question about passing along knowledge, but just to
this is just what piece of human wisdom, like Richard Feynman, your fellow laureate, said, the atomic hypothesis is the sum in the most content of information in the fewest words. What would you brag about that we've learned about, you've learned about, or anything that humanity would brag about to tell alien civilizations a billion years from now to brag a little bit about?
Yeah, so if it was like that I wanted to tell something that was a piece of scientific knowledge, it would be that, in fact, nature follows regular, discoverable, mathematically expressible laws. The fact that that's true is, in some sense, absolutely astounding.
Magical.
And people, I mean, I would say that the understanding of the truth of that, in a sense, is the content of the scientific revolution. So maybe there's one other thing, and that is what I think is the content of the scientific method. People often have some formal thing for what the scientific method is. I think that's garbage.
Yeah.
Key thing about the scientific method is that truth is determined by the way nature is. Nature is the final arbiter of scientific truth, not thinking about it and deciding this is, sounds good, but is this the way nature actually works? I think that is the substance of the scientific method. You observe and you experiment, and that's the thing that determines whether you got it right.
Yeah, and then I always note that there's not just one scientific method, which is not very scientific if you have multiple, but you should come to the truth, and you should have consensus. You shouldn't maybe have uniformity, as you know, in the Old Testament. If all the judges on the court found the accused party guilty, he or she was set free, because like somebody didn't do their job defending the other side quite adequately. Okay, we're going to go one more question for you, and this is Arthur C. Clarke, as you know, had many laws. A very famous one that you at NIST embody, which is any sufficiently advanced technology is indistinguishable from magic. He had another one that I drop on my department chair from time to time, which is for every expert, there's an equal and opposite expert. I like that one. But last one is the third law says the only way of discovering the limits of the possible is to venture a little way past them into the impossible. And that is the origin of the name of this podcast. And I want to ask you, Bill, kind of advice to your former self as a young person, a 20-year-old, a 30-year-old. I've asked Nobel laureates like your friend Barry Barish. He told me he had the imposter syndrome when he collected his Nobel Prize. I guess you have to sign this little document that says you got your prize, a binder. And he saw this guy's name, Albert Einstein, and he said, I'm not worthy. He had the imposter syndrome. I pointed out Einstein had people that he looked up to, like Newton and so forth. But what advice would you give to your former self? And secondly, I'm curious, have you ever had the imposter syndrome?
So I'll answer the second one first. Yes, absolutely, all the time. Whenever I go to a talk and hear people talk about this and that I think, my gosh, I should have learned that. I should understand what he's talking about. Oh my gosh, I'm going to have to go back and learn that. I'm just not in the game. That happens to me all the time. Okay, so now what advice would I give a couple of things. Don't trust everything that people tell you.
Like what?
And here I'm thinking especially of theorists.
Mm-hmm.
Because they only know what they know. And when we're going to make progress by finding out that they were wrong.
Mm-hmm.
And I think that there is a tendency of thinking these guys are pretty smart. And they've figured everything out right, and other people have checked it and it's right, and not always.
Yeah.
So part of that story is that now fast forward a little bit to when I'm in my late 30s or early 40s, I forget when, probably about 40, we measure the temperature of the atoms after laser cooling, and we get just what we expected. And then we measure some other stuff, and it's not working out right. And so I go to a theorist and I say, we got these crazy results. And it could be, if the temperature were a lot lower than what the theory predicted, it might be some of these results would make sense. Is there any way that that's possible? I said, absolutely not. On general principles, I can show that the temperature, there's no way the temperature can be lower. On general principles. And I said, okay, fine. So a few months later, we measured the temperature, and it was way lower than what the theory said was the lowest possible temperature, in spite of the fact that all these theorists said that there was no way it could be lower, and that they had very general arguments saying that it had to be this. And so don't pay that much attention to what people tell you they think is true. Another thing is, we're taught when starting to do an experiment, we should really think it through very carefully. Ask about how big the signal noise is going to be, what's going to happen, how we're going to put it all together. If we had taken that seriously when we started doing laser cooling because we wanted to make a better atomic clock, we would have given up right at the start. Because what the theory told us we could do for the lowest temperatures was not going to be good enough to make a decent atomic clock. And we never would have. But we just said, this looks like fun. Making things cold with a laser just sounds like fun, because it ought to, you ought to be, you shine a laser on something to make it hot. If we can make it cold by shining a laser on it, that's just really neat. So let's just do it. And it turned out that all the roadblocks that we would have taken seriously, if we'd done things very carefully, just disappeared. That it's easy, or at least easier, to figure out all the reasons why things are going to go wrong than it is to figure how you're going to fix it when you're right in front of it. That it's really hard to know what to do with something until you're holding it in your hand.
And literally, in that sense, you went into the impossible. You had courage. It takes courage to go against, the advice of senior colleagues. Perhaps you were saying you were in your, early stage in your career. It took a lot of courage to go against it. It reminds me of the final famous quote by Arthur C. Clarke. He said, "When an elderly, distinguished scientist says something is possible, he's most likely, or she's most likely, right. But when they say it's impossible, they're most likely wrong." What do you think now is, if you were a grad student and you're starting at Maryland or UC San Diego or anywhere, what would you do if you and I said you can't do what you've done, you have to go completely orthogonal to what you've done. I'm just curious, Bill, what would you do? What's exciting to you?
One of the things that I find absolutely astoundingly interesting is cell biology. It just seems like so much new stuff is happening so fast. I mean, look at these mRNA vaccines. That would have been impossible without the things we've learned about the genetic code in the last years. And look at how wonderful those vaccines were, much better than anybody dared dream. And
Great. Well, Bill, I want to thank you so much for sharing so much of your time with us. I hope someday we can do a part 2 on the future of where we're going at the timekeeping. We had such a delight learning from you. You're kind of the type of professor that I wish I could have had growing up, and that I aspired to be. And with guests like you as inspirations, I think you do inspire more people than you can possibly imagine. So, Bill, thank you so much. Enjoy the rest of your day, and thanks for coming on the podcast with me.
It's been a pleasure.
Any sufficiently advanced technology is indistinguishable from magic.